So during the last lecture, Nuo should have, I think he finished, got to the last slide, or I'll come back to this, because I know he didn't quite finish that. Let's see. Okay, so the content of the last lecture was summarized in this slide. Okay, so there's basically two regions of operation for a MOSFET, a linear regime, or region, and saturation region. So what is the biggest, what delineates the boundary between, what delineates the boundary between linear and saturation mode of operation? VD-sat. So it's VD-sat relative to something. VGS, right? So in the linear, okay, this is like, this pen is dying. Peng, can you get a pen for my office, please? Yeah, thanks. Okay, so in the linear regime, basically VDS, the drain to source voltage, is relatively large, right? So it's larger than VGS. My goodness, this is really bad. VGS minus VT, but because of the body effect, right? The fact that the channel actually is biased at some potential above ground. So there's a channel inversion layer to body bias. You actually have more depletion charge than ideally predicted. So you actually have this body effect factor there at the bottom. Thank you. All right. All right. So in the linear regime, the drain to source voltage, is smaller than VGS minus VT corrected for the effect of the body depletion charge. Okay, so so in contrast, in the saturation regime, or region of operation, the drain to source voltage is greater than VGS minus VT, corrected again due to the body effect. So what this means is that the channel inversion layer is pinched off at the drain end. So the inversion layer only exists partway through. Let's say for an N-channel MOSFET, inversion layer of electrons sort of ends before it reaches the drain junction. Okay? So just qualitatively, just remember that saturation means that the transistor is having to hold a pretty large drain to source voltage such that you can't actually form an inversion layer all the way from the source to the drain. Okay, so what's an easy way to remember these current, so for the exams, it's good to know these current versus voltage equations. So it's actually summarized here. Let's just, you should be able to derive this very quickly if you forgot, let's say if you forget to write them down in your notes. So we know the current flowing between the source and the drain is proportional to the width of the channel, right? The wider the channel, the more current you can conduct in the on state. And it's proportional to the amount of inversion layer charge that you have per unit area. And is proportional to the velocity, the average velocity with which carriers are drifting in the on state from the source to the drain. So this is W. Let's look at Q inversion. So Q inversion is Cox, or the equivalent gate oxide capacitance, times VG. Okay, it's VGS now. We're referencing all of our gate voltages relative to the source voltage. So VGS minus VT. Okay, that's true at the source end, right? At the drain end, the channel in the, okay, let's say we're looking at the linear regime. The channel potential goes from the source potential up to the drain potential, right? Starts at the source potential on the left, goes to the drain potential at the right. So on average, this is an easy way to remember. On average, the channel inversion layer is like halfway between the drain and source voltage. So we have this minus VDS over 2 factor. Okay, but because of the bulk, charge effect, you have even less inversion charge than the ideal case. Okay, now what gives us the average drift velocity flowing from the source? So it's basically mobility, the effective mobility times electric field. Okay, so what is the electric field that's driving carriers to drift from the source to the drain? Yeah, so it's just VDS over L. Okay, so let's see, did I forget anything? I think that's pretty much it. Let's see. Okay, so here, yeah, so if we look at this slide, that's pretty much the equation you get, right? Yeah, that's right. So hopefully, qualitatively, you understand where this equation comes from. Now, that's in the saturation regime, right? When the electric field across the inversion layer is just equal to VDS divided by L. But in the pinch-off regime, you're not applying the full VDS across the inversion layer. Okay, so let's say you have the source voltage, and that's the reference voltage. You're applying a gate voltage relative to the source voltage. What is the voltage of the electric potential, or what is the potential of the inversion layer right at the pinch-off point? VD sat, that's true. So the voltage right at the pinch-off point, so this is an important thing to remember, is VD sat, okay, so which is equal to VGS minus VT, and it's less than that because of the body effect factor. Okay, so in saturation, ID, so this is so now in saturation regime, it's linear regime. Have W mu effective, still have C ox equivalent times VGS minus VT, but now instead of VDS over L, it's VG, well, VD sat over L. Okay, so anyway, and another, it turns out to be 2M, if I remember correctly. 2ML, yes, right, you forgot the L. Forgot the L there. Okay, so basically, this you can probably work the algebra out here, but it's basically the same thing, except now the maximum voltage you can apply, which determines the drift velocity, the electric field, and therefore the drift velocity, is going to be limited to be VD sat. So no matter what the drain voltage is, the voltage drop across the inversion layer is just equal to VD sat. And any extra voltage above that is dropped across this pinch-off region. Okay? All right, so qualitatively then, if we have very low VDS, then we can use the equation for the linear regime. And if VDS is very small, then this last term in the parentheses becomes negligible, or compared to VGS minus VT. So we can actually plot current. When we measure a real transistor, we can plot the current, ID, with applying, let's say, a few tens of millivolts of VDS. Okay, so 50 millivolt difference between the source and drain. We can measure the current as a function of the gate voltage. And then we can, as illustrated here, you would end up with sort of a data points that fall along a straight line. And you can extrapolate down to zero current. And technically, at zero current, that's where the gate voltage is equal to the threshold voltage. So experimentally, we can actually determine the threshold voltage of a MOSFET this way. Okay, any questions left over from the previous lecture? Let's go on to the lecture today. So now we're going to talk about, again, well, in complementary MOS technology, we have both N-channel and P-channel devices. So we'll review P-channel devices very quickly here, and then go back to the CMOS inverter to see how it's used. First, looking at a digital logic, using it as a digital logic kind of a device or a circuit. And then the small signal model is really relevant if we want to use MOS transistors for amplifiers, rather than like analog amplifying analog voltage signals. So CMOS inverter analysis is really more relevant. The analysis we're going to do here is more relevant to digital logic applications, but then we'll also touch upon analog circuit applications. So a P-channel MOSFET operates in a similar manner as an N-channel MOSFET. It's just that when you turn it on, you have an inversion layer of positively charged mobile carriers at the surface of the semiconductor. Oops. So when you turn it on, there are holes, right? There are holes that are sort of attracted to the surface. Actually, not attracted to the surface. What happens, okay, technically, is you apply a negative voltage that is more than a threshold voltage below the flat band, the gate voltage is lower than the source voltage by more than the value of the threshold voltage. Okay? So the gate is more negative than the source voltage. So that will cause the surface to become inverted, to be P-type. So holes can easily flow from these heavily doped P-type source and drain regions into the channel region. Okay, so holes can actually drift from the source to the drain. If there is a voltage difference between the drain and the source, that causes holes to drift to that side. So the definition of the drain, is basically determined by the voltage that you apply. Okay, so the drain, okay, so there's going to be a difference between the voltages, between the source and drain. Which one is going to be the drain in an integrated circuit? The one at higher voltage or the one at the lower voltage? Lower voltage, right? The lower voltage is where a positive charge would like to flow. So that's why the VDS, which is defined, again, to be VD minus VS, that's negative. And current in this field for a transistor is always defined to be, in this case, defined to be positive if it flows into the drain. That's just a convention. So if you have holes flowing from the source to the drain and they flow out into the circuit, you have positive charge going in the direction opposite of that for positive current. So that means that, just according to this convention, drain current for a P-channel device is negative. Okay, it's just because of this definition, this convention. But just like in an N-channel MOSFET, if you increase the difference between the gate voltage and the threshold voltage to invert the surface more and more, you'll get more and more inversion layer charge density at the surface, so you have more current. The magnitude of current will increase. Okay? And if you have more drain to source voltage, then the drift current or the drift velocity will increase and you have higher current up to the saturation value. And in a CMOS technology, usually the N-channel and P-channel devices operate in a complementary manner, as I mentioned last week. And the threshold voltage is typically similar in magnitude. So anywhere from 0.2 on the order of, so VT for N-channel MOSFETs are anywhere in the range of, let's say, 0.2 to 0.5 volts in modern CMOS technologies, the state-of-the-art CMOS technologies today. Okay? Because the supply voltage, the maximum voltage used in a circuit is typically around 1 to 1.5 volts. So the current versus voltage equation for a P-channel device, and I think there's an error here. Basically, we know the current, according to the convention, is negative, right? So if VGS is negative and the threshold voltage is negative, well, this term will still be negative. And certainly, and then VDS is negative. So this is sort of reducing the magnitude of the quantity in the parentheses as you expect. So I think this is supposed to be positive because we know IDS should be negative. Okay? And then in the saturation regime, again, the maximum voltage you can apply across the inversion layer of holes, in this case, it's just VGS minus VT, corrected by that body effect parameter. Okay, so the equations look very similar. Just keep in mind we're applying gate voltage that's lower than the source voltage, and the current is not flowing into the transistor, into the drain. It's flowing out of the drain. Okay? All right, just qualitatively, are there any questions? Okay, so now let's look at a digital logic circuit. So looking at a MOSFET used for digital logic. So again, this is what we went over this last week. That a CMOS inverter comprises just two transistors, one NMOS and one PMOS. And the key is that the gates are tied together, electrically connected. So whatever voltage, whatever signal you want to apply to the inverter, it goes directly to the gate of each transistor. And then the drains are tied together, and that way they can drive the output voltage to be either high or low, depending on the input. Now, in steady state, ideally, if the input voltage is not changing and it's, let's say, high, then at the highest possible voltage, that's the supply voltage, VDD, then the PMOS device will be off, NMOS device will be on. What is the voltage difference between, what is VDS for the NMOS device? So let's say VDS is small, okay? And what is VDS for the PMOS device? It's large. Okay, that's good. And then you have the opposite case here, right? You have VDS is large. For the NMOS, if the input is low, so the NMOS is off, and then the PMOS is on. So output is connected to VDD, and the VDS value is small in this case. Okay, so one key thing to note is that if there's any leakage current, so even though a transistor is off, in reality, there's always going to be some non-zero leakage current. So there's actually going to be some I off flowing through here, okay? Off-state current flowing through. So I off for the PMOS, I off for the NMOS in the opposite case, okay? So basically, even if your CMOS circuit is not doing anything useful, it's just holding this steady state, it actually can consume some non-zero power. And the amount of power that's consumed is basically proportional to the current times the voltage. And so that means the standby power is going to be proportional to I off times VDD. So if you want to minimize power consumption, which usually is a good thing, you want to minimize I off. And it helps if you can lower the VDD. Okay, so that's one thing we'd like to do is as we advance technology, we'd like to be able to make transistors that can operate at lower supply voltage and have very, very low off-state leakage. Okay, we're going to come back to this later because in reality, it's not easy to do that. Okay, so let's see how a CMOS inverter actually operates if the input voltage is changing. So to understand that, we need to take a closer look at this voltage transfer characteristic, which shows how the output voltage, depends on the input voltage. So last week we looked at in the previous slide we looked at two steady states. If the input is high, NMOS is on, connecting the output to ground. And if the input is 0, then the PMOS device is on, connecting the output to VDD. So let's see what happens if we actually apply an input signal that's time varying, so the voltage can be anywhere between 0 and VDD. Okay, so just qualitatively, as we increase the input voltage, eventually the input voltage will be greater than the threshold voltage of the NMOS device. And so the NMOS device will start to turn on. Okay? So if the NMOS device starts to turn on, just qualitatively, it's no longer like an open circuit switch. It's on, but so it has some kind of resistance to current flow. And initially, that resistance to current flow is pretty large. It's larger than the on-state resistance of the PMOS device. So let me just draw it here. So here we have in this regime, we have the resistance of the PMOS device connected to VDD. Here's V out. And then we have some resistance of the NMOS device, because now it's on, right, connecting it to ground. So the output voltage is just going to be given by the voltage divider formula. It's going to be somewhere between VDD and ground. And initially, when you turn on the transistor, the NMOS transistor, R sub n is going to be relatively large compared to R sub p. So V out will be closer to VDD than to ground. Okay? Does that make sense? Okay, so qualitatively, that might be a little confusing. So let's see. Let me go back. Go back to this slide here. Okay, so when the NMOS device first starts to turn on, when you increase the input voltage and it starts to turn on, what regime of operation is it in? Saturation, exactly, right? Because it starts out with large VDS, right? So if VDS is large and VGS is just turning on, so as VGS is slightly above the threshold voltage, you're going to be in the saturation regime. Okay, and the reason, so the amount of current that the NMOS device will want to conduct is going to be proportional to VGS minus VT. So if VGS is not too far above VT, then the current that it wants to conduct is relatively small. In other words, the resistance, effectively, you want to model it as a resistor, the resistance is relatively high. Okay. Okay. Right, so that's why the voltage is still closer to VDD than to ground when the NMOS is just starting to turn on. Let's go to the other extreme. Let's start with the input is at VDD. So you start out with the PMOS device off, and the NMOS device that is in the linear regime is on. Okay. So let's say we lower the input voltage from VDD down, and let's see. So how much do we have to lower it down to enter this second regime here? Going to be equal to the threshold voltage for the PMOS device. Okay, so once the input voltage goes below VDD minus VTP, then you start to see that then there will be more, the gate to source voltage of the PMOS device will be more negative than VTP. So then you start to see the PMOS device turn on. And again, you have a voltage divider effect. But similarly, the PMOS device, when it's starting to turn on, when you lower the input voltage, it's operating in the saturation regime. And it's going to have higher effective resistance than the NMOS device. So the current is, the voltage is going to be closer to ground than to VDD. Okay, so basically we're going to go through an analysis. This might be a little confusing, but there's a point to this. So this is going to take a few slides. All right, so let's look at the CMOS inverter in EE1, or the equivalent of EE40. Maybe you've done something called load line analysis. So this is where we have two devices in series, and if the input and output doesn't have any current flowing, out or in. Okay, so in steady state, if the input and the output are not, well, if there's no current flowing in or out from the input and output nodes, if that means, sorry, from the out, there's no current flowing this way. Okay, so I this way out equals 0. So for the load line analysis, basically what we're assuming is that the current flowing through these series connected devices is equal. Okay, it's equal in magnitude. All right, so what we do then is we plot the behavior. Okay, so these IV curves specify for a given applied voltage, so for a given applied gate voltage and a given applied drain voltage, what is the current that flows? Okay, that's what these IV curves represent. So what I've plotted here are the IV curves for the N-channel device. Okay, so it's just the drain current of the N-channel device as a function of the drain to source voltage of the NMOS device. Now, if you look at the inverter circuit, the drain to source voltage of the NMOS device is equal to the output voltage. And, okay, well, that's good enough. Okay. And as you increase the input voltage, you're increasing the gate voltage directly of the NMOS device. So that's what this blue arrow represents, right? Because increasing Vin is equal to increasing VGS. Okay, so that's easy for the NMOS device. Now so now what we want to do is on the same plot, okay, of plotting the current versus the output voltage, we want to plot the IV characteristics for the PMOS device, okay? And then we want to find the points where the PMOS current equals the NMOS current, and that will tell us where the stable operating point of the circuit is, right? Because in steady state, the current flowing in the PMOS has to equal to the current flowing through the NMOS. Okay, so let's do that. So to do this, we have to figure out, okay, how do we translate these voltages? So Vout, how does that relate to VDS for the PMOS device? Okay. And then secondly, we have to find out, okay, how does the input voltage relate to the gate voltage of the PMOS device? So we can plot it on the same plot. So to do this, we make a couple of observations. So first of all, we can see that the input voltage is going to be, okay, so here's this plus minus, this is VGS for the PMOS device, right? The gate voltage minus the source voltage, right? That's the source. So we can see that the input voltage, VDD, if we start out VDD and we add this voltage drop here, if we add VGS for the PMOS device, we should get Vin. Okay, so that's what this first equation states. So what then this implies then is that the gate to source voltage for the PMOS device is just equal to Vin, but you have to subtract VDD from it. Okay? Okay, I'll come back to that in a second. How about the output voltage here? The output voltage, let's see, again, we start with VDD. Now we add this voltage drop here, then we can get the Vout. So Vout is just equal to VDD plus this voltage difference here from the source to the drain, or sorry, the drain to source voltage drop for the PMOS device. Okay, so that's how we get this equation, but then we can invert it to write an equation for VDS. Okay, so the drain to source voltage of the PMOS is just equal to the output voltage minus VDD. Okay, so if we account for that, then you can figure out that the IV curves for the PMOS device look like this. Okay, so let's see if this makes sense. I think a couple of, right. So if the output voltage is at VDD, then the drain to source voltage for the PMOS device is 0. Okay, right here. And if the output voltage is equal to 0, okay, so if the output voltage is 0, then we're at the origin here, but that's where the drain to source voltage for the PMOS is largest, it's most negative. Okay, so basically it's like the IV curve, but you flip it, horizontally across like this. Now, in terms of these curves, as these curves correspond to increasing gate overdrive voltage. In other words, more VGS minus VT, the magnitude. So the uppermost curve corresponds to input voltage of 0. So if the input voltage is 0, then the gate to source voltage is the highest, right? It's negative VDD. That's the most negative it can be. And as you increase the input voltage, you're actually decreasing the negative value of VGS for the PMOS device. Okay, so as the input voltage increases, you actually are going to move to lower and lower curves on the IV characteristic for the PMOS device. Okay, so that's basically how you can map the IV curves on the same plot of current versus output voltage for the NMOS and PMOS devices. Okay, so now let's look at just a few of those regions in the transfer characteristic. So let's look at region A. Okay, let's start with something easy. Region A is starting at very low gate voltage, so the NMOS device is off. So if NMOS device is off, that means the input voltage is less than the threshold voltage of the NMOS device, and so the current should be 0 the NMOS device, for all drain to source voltages, ideally. Okay, but if the input is low, that means the gate to source voltage is very large for the PMOS device. So it's on this kind of high curve like this. But the output voltage is kind of high. So yes, we have to be somewhere operating along this curve, but the current for the PMOS device has to equal the current for the NMOS device. And the only way that that can be is if you're operating the PMOS device at this operating point here. Okay? So that's the operating point in the region A. Now, as you increase the input voltage to turn on the N MOSFET, okay, so now we have a low VGS minus VT. Okay, so it's like some low curve like this. Then the gate overdrive for the PMOS device goes down, okay, and so you basically have a lower curve for the PMOS device. Again, the currents for the two transistors have to equal, so the operating point of the circuit, the steady-state operating point of that circuit is at the intersection. Basically, it's where you have to satisfy both requirements for the two devices. Okay, so notice now the output voltage, V out, has dropped a little bit, right? So V out is close to VDD, but it's a little bit below VDD. Okay, let's hop over to the case where the input voltage is now pretty close to, it's now getting high. So the PMOS device actually has very little gate overdrive. And so you have an even lower curve, this yellow curve, for the PMOS device. In the meantime, the input voltage is going higher, so the NMOS device is actually, the VGS is higher. So now you have to look at a higher VGS curve for the NMOS device. And again, the stable operating point is where both currents are equal. So notice for large input voltage, the output voltage goes close to 0. Okay? And then finally, when the input voltage is greater than VDD minus the VTP magnitude, then the PMOS device is off. So now the PMOS device has to have 0 current. The NMOS device has to operate somewhere along this high current curve, but the only way you can satisfy both the requirements for NMOS and PMOS current is where these 2 points intersect. So that's basically at the origin. So output voltage is there for 0 if the gate voltage is high enough so that the PMOS device turns off. Okay, so the reason I'm going through this is because this determines actually how fast a CMOS circuit or a digital logic circuit works. Okay, so I'm plotting. So now let's just look at a single. Okay, let's go back. Okay, so this is kind of like flashing slides quickly, but if the input is low, we start with a high output voltage, and then as you increase the input voltage, you see this current starting to flow in the NMOS device. Okay, as the output drops, and eventually the output drops close to ground because the NMOS device is connecting the output to ground, and you end up operating the NMOSFET in linear regime, and essentially you hit steady state when the output goes all the way to ground. Okay, so let's look at just the NMOS device. Okay, so these are the IV curves for, let's say, an NMOS device. And now let's see how an inverter actually might work dynamically. Okay, so one thing that we will just refer to simply is ID sat. So the saturation drain current, let's just define it to be very simply the maximum current that the NMOS device can conduct. So that's with maximum drain to source voltage equal to supply voltage, and maximum gate voltage equal to the supply voltage. So let's look at like a digital logic circuit. You usually have input signal driving the input, the output of some logic gate driving the input of the next stage. Okay, so a simple example here is just inverters connected in series like this. Okay, so each of these symbols, these inverters symbols here just represents 2 transistors connected in series like this. Okay. So let's assume that the input voltage you want to suddenly pass a 1, like a high voltage. So you increase the voltage at the input of the first inverter. So over time, the voltage at the input here will increase. And that will cause the NMOS device to turn on. to discharge any capacitance here. So usually there's always going to be some capacitance, and that's covered on the next slide. There's always going to be some charge that you have to move off this output node in order to change the voltage. Okay? So basically that charge is going to flow through the N MOSFET, and once you discharge that load capacitance, then you can bring the output voltage down to 0. Okay, so that's what's shown here. V2, the output of that first inverter drops with time. Okay, so it starts to drop after the input voltage goes up. So one thing that the industry likes to keep track of is the propagation delay. So that's T or tau sub P for the propagation delay. How long does it take for the results of the input, any change in the input, to propagate to the output voltage? And usually we measure it from the 50% point. So when the input voltage changes to be like halfway up, to VDD, how long is the delay until the output drops halfway down? Okay, so that's the propagation delay for high to low transition. So when we first let's see, where do we first start? So let's assume very simplistically that the NMOS device starts to really conduct significant current to discharge this load capacitance when the input voltage reaches 1/2 of VDD. Okay, that's the current. I mean, that's the value of voltage that we care, to measure the time from, or the delay from. Okay, so that means we start here. All right. So once you turn on the transistor, the NMOS, what happens to the output voltage? It starts to fall, right? So it starts to fall. That means the output voltage here starts to go towards 0. But that's happening at the same time that the input voltage is still rising. Okay, so that means over time you're actually going up to a higher curve, but the drain to source voltage is, well, you're going up to a higher, gate to source curve, but the output voltage is going down. So basically, dynamically, your transistor is starting out at this point here, and then at this point in time, it's operating like here. Does that make sense? So over time, your transistor basically turns on and conducts current, and once the output voltage drops enough, you end up discharging the rest of the way, maybe mostly in the operating the transistor in the linear regime. Okay. So the question is, what is that delay? Okay. Well, the delay basically is due to the time it takes to discharge this whatever capacitance is on the output node. So remember that the current is equal to C dV dt, right, for a capacitor. Right, so if you want to change the voltage more quickly, you need to conduct more current. Does that make sense? And if you have a large load capacitance, then you need more. It takes more time to discharge the output. Okay, so the question is, what is that? So what is the current? If we want to take the average effective current, so this is what the concept of I sub EFF, that's effective drive current of the transistor. It's just the average. We're just simplistically saying it's the average of these two current points. Okay, so the average of the current operating in the saturation, but with relative, not very high VGS. And then, okay, so VGS is half of VGS minus VT. Let's see, so this is VGS is equal to 1/2. Oh, okay, that's what's said here. And here, this is VGS is equal to VDD, but VDS is equal to VDD over 2. Right, so here, VDS equals VDD. Okay, does that make sense? What you really want to do is you want to make your circuit operate more quickly, to minimize that propagation delay. You want to have more current flowing to discharge that output load capacitance. That means you need to maximize the average of this I sub L and I sub H. Okay, so that's what determines the speed of your circuit. Okay, so if you look at the current versus voltage equation, let's go back and take a look at that. how would you okay, so most of the time the device is operating in the saturation regime, right? For that digital circuit. Do I have that here? So what's the best way to get large IL and IH? If you had to design your transistor, well, okay, you can make it wider and shorter gate length, but there's limits in how short you can manufacture a gate length. If you have a wider transistor, actually you end up with more gate capacitance, and so, okay, we'll talk about that later. So that's not desirable to make larger devices so you have more capacitance in your circuit. What else can you do to speed up your circuit, your digital circuit? Yeah, so you want to shrink the thickness of the gate oxide so you can have higher capacitive coupling between the gate and the channel. I mean, in other words, you have more voltage applied across, to the channel. And in any case, you have more inversion layer charge density, right? If you increase Cox equivalent by thinning down the gate oxide. Okay, what else? Better material, like maybe higher mobility. Okay, so in recent generations of technology, people have come up with novel ways to enhance the effective mobility of electrons traveling, or holes traveling from the source to the drain. So we'll talk about that probably next week. What about this? How would you choose VT? Right, so low VT, right? Ideally, low threshold voltage means higher drive current, higher saturation current, so higher speed circuits. Very good. So in the design project, which is actually now posted online on the class website, I think the EE130, the undergrad students will ask you to design something that has a relatively low VT. So it's a high performance transistor. For the grad students, we're going to ask you to design something with high VT, and we'll explain why. And it turns out it's harder to design something with high VT. That's why it's reserved for the grad students. Okay. Oops. Any questions about this, just qualitatively? No. Okay, so propagation delay. I just wanted to mention this load capacitance. Okay, we're just explicitly drawing it here. It's not something that we purposely add. Like, we don't really ever purposely fabricate a capacitor right there at the output node of any digital circuit. But basically, it always exists. Okay, so so where does that capacitance come from? That's the question. There's 3 different components of that load capacitance that always exist. Gate capacitance, very good. So let's call that number 1. So the gate capacitance of the next logic gate, and you can actually have the output output signal of one logic gate feeding multiple logic gates. Okay. So yes, when right here you have the gate oxide, right here, right? So you basically have some gate capacitance for those transistors, and you have to charge or discharge the voltage on those gate electrodes to change in order to make a change in the output voltage here, right? Because it's all electrically connected. Okay, so that's one source. What's another source? Okay, so there's the interconnect capacitance. Very good. So these these metal wires that connect, let's say the drain of those output of these transistors. Okay, that's semiconductor material, right? So you need to have a wire, some kind of metal wire running to physically contact the drain regions, and then wire and connect it to the gate electrodes of the next stage. And the wire runs over the silicon substrate, so there's some capacitance. There's some insulating material, of course, between the wire and the silicon substrate, but there's capacitance there. So that's good. One final source of capacitance, small signal capacitance. Yes, Justin? That's right. So it's junction capacitance. So it's the drain. Okay, so both the PMOS and NMOS devices have drain to body junctions. They're reverse biased, anyway, but they have small signal capacitance, right? In order to change the voltage on a PN junction, you have to add charge or remove charge. And that, so it takes time to flow the charges in or to take them out, and that's what adds to the extra delay, right? So those are the sources of capacitance in any digital logic integrated circuit. So before, when I was talking about making a circuit faster, if you make the transistors larger, wider channel length, yeah, that will conduct more current, but that also adds to the load capacitance. So that's not necessarily the best way to speed up a circuit. Okay. So technically, this I effective is really kind of the average. If we're looking at the propagation delay, we just take the average of the the high to low transition. Oh, sorry. Yeah, high to low output transition, and then the low to high output transition. So there's, if you notice, there's like two slightly different delays. So if we just look at two inverter delays and call that the average of those, high to low and low to high transitions, take the average, then that means we're taking, I effective really is the average for the NMOS and PMOS device. Okay. So this analysis that I showed here, we can do the exact same analysis. But this is really an analysis looking at the output, having the N-channel device turn on to discharge the voltage, high output voltage to 0. You have the same thing happening for a PMOS device for a transition. If the input goes from high to low, you have the PMOS device turning on and going through a similar, similar kind of a trajectory on the current versus voltage curve. So the PMOS device also has an I effective. Okay. Any other questions on digital logic performance? Okay. So we learned about the speed. Okay, how to make a digital circuit operate faster. Let's talk about that off-state leakage current. So this is often called the sub-threshold leakage current because the gate to source voltage is smaller than the threshold voltage. So certainly when the gate to source voltage is less than threshold voltage, ideally the transistor should be off. But in reality, there's always some current flow. So when a MOSFET is turned on, you form an inversion layer, and the current is limited by the speed at which carriers can drift from the source to the drain. When the transistor is off, current actually flows, but is limited by the rate at which, okay, so when the transistor is off, remember this is still a drain to source voltage. So carriers can always drift very quickly across the channel. But the current is actually limited by the rate at which the carriers, electrons in this NMOS case, can actually diffuse into the channel. Okay, so in the off state, just remember in the off state, the current is limited by diffusion. In the on state, current is limited by drift. Okay, so let's draw the energy band diagram, or actually just the electron conduction band diagram. So let's look at EC from the source to the drain. Okay, so there's some voltage difference here, and that's why electrons would like to go to the drain. But if the gate voltage is 0, then the semiconductor underneath the gate electrode is actually kind of p-type, or it's depleted, depleted p-type material. So basically, there's a potential barrier for carriers to flow from the source into the channel region. Once they get into this channel region, then you have an electric field that allows them to drift to the drain. Okay, so this barrier height, that is what we control with the gate voltage. Okay, so if we increase the gate voltage for an N-channel device, we're basically lowering the electric potential for electrons, and so we lower the potential barrier. So basically, when a transistor is operating below threshold, as you change the gate voltage, what you're doing is you're changing the potential barrier for diffusion. So this should sound familiar because for a p-n junction, as you change the voltage across a p-n junction, you're just modulating the potential barrier, right, for diffusion. Except the only difference here is in a MOSFET, you actually don't have direct contact to the p-type region here. You're actually only able to control the potential of the p-type region by capacitively coupling, through this MOS capacitor. Okay. All right. So right here. Anyway, so basically it's a capacitive voltage divider effect. Okay. So you have this gate voltage that you can change, and as you change the gate voltage, you're changing the channel potential. Oh, okay. There might not be an inversion layer yet, but you're changing the potential at the surface of the silicon. Okay? So here's an oxide. So you're capacitively coupling to the channel potential through the gate oxide. And then you have some depletion region in the silicon, so you have some depletion capacitance. Okay, so this is a simple voltage divider kind of a circuit. Okay, so as you're changing the gate voltage, yes, you are making a change in the channel voltage, but because of the voltage divider effect, the change in the channel voltage is going to be less than the change in the gate voltage. And it turns out then you see this body effect factor here. Okay, it's the same as that. Okay, so as you change the potential barrier height for diffusion of carriers into the channel, let's plot this. So let's plot this is like from the first part of this course. Let's look at the density of electrons. And this is the conduction band edge, okay, as a function of energy. So remember, it looks something like it's exponentially decreasing like this, right? Okay, it's not a great exponential. But anyway, okay, so this is actually very close to the conduction band edge, right? It's 1/2 kT. Okay, so it's I'm not drawing it very precisely, but okay, so just an exponentially decaying function like this. Okay, and basically, let's say there's this barrier height. Only these electrons have the kinetic energy to diffuse into the channel region. Okay? So you basically can integrate the concentration of electrons as a function of energy for all these energies above this energy here, right? And that will tell you how much leakage current will flow. Okay. So as you change the gate voltage, what you're doing is you're changing the barrier height. So if you, let's say, lower the barrier height by a little bit, let's say, so we lower the barrier height down to here, right? Then the integrated charge, the integrated concentration of electrons that can make it over the barrier increases exponentially. Okay, so this is exactly the same description of how current increases exponentially in a p-n junction. Okay, so if we plot the current on a log scale then for a MOSFET versus the gate voltage, then you'll see something like this. So below the threshold voltage, you're going to see an exponential dependence of current on the gate voltage. And above the threshold voltage, where the current becomes limited by the rate at which carriers can drift, it becomes more linear like before. Okay, so above threshold, it's more linear, right? And then below threshold, you sort of have a log dependence of current on the gate voltage. Okay, so a parameter that people will like to report when they talk about advanced transistor technologies is the subthreshold swing. Okay, so that's S, and that's defined to be the amount of voltage change, the gate voltage change needed to cause the transistor current to change by 1 decade. In other words, by 10x. Okay, so do you remember what the slope was for a diode? 60 millivolts per decade. That's for a diode. Now, a transistor should be worse, right? Because you can't directly connect to you don't have direct connection to the p-type channel region. So you imperfectly can control the channel potential. So is a subthreshold swing going to be more steep or less steep than for a diode? It'll be less steep, right? Because you need to apply more change in gate voltage to get the same change in potential barrier height compared to a diode. So that's exactly right. So if you look at this equation, this is 60 millivolts at room temperature per decade. But now it's worse because of this capacitive voltage divider. Okay, that's basically it. So okay, so I already went over that. So then fundamentally, there's a trade-off when you want to specify the threshold voltage, because as we just talked about, you would like to have low threshold voltage to have higher drive current for faster circuit operation, digital circuit operation. So next week we'll talk about short channel devices. So eta, this exponential, this power factor here, is closer to 1 for very short channel devices. And for long channel devices, which is what we've really been focusing on so far, this eta is 2, right? Long channel. But in any case, the lower the threshold voltage, or the smaller the threshold voltage is, the more current your transistor flows. So the faster your digital circuit should operate, or the smaller the propagation delay. But if you have lower threshold voltage, what that means is that your off-state leakage current is going to go up exponentially. Right? So when the transistor has 0 gate-to-source voltage, you have some non-zero leakage current flowing. And if you lower the threshold voltage, you're going to increase, you end up with exponentially higher off-state leakage. Okay, so for that reason, the industry has not been able to aggressively scale down the threshold voltage to be too close to 0. Okay, so for high performance applications, where it's more important to have high speed rather than low power, then we can tolerate a lower threshold voltage, higher leakage. But if you really just care for low power applications, then really need to operate with higher threshold voltage, so you don't waste power, when the circuit's not doing anything. Okay, so clearly, this trade-off can be alleviated if, well, why don't we just have a transistor that can, have low off current and high on current like this at low voltage? I mean, why don't we just, wouldn't this be good? We can have high drive current and low off-state leakage. Okay, so bottom line is, what are we doing to the subthreshold swing here? We're making it steeper. We're trying to make it smaller, right? So the question is, well, how do we, so in other words, we want to be able to change the current with less change in gate voltage. Or either that, or we want to turn off the transistor more quickly as we lower the gate voltage. So the question is, how do we minimize that subthreshold swing? How do we make it steeper? Yes, Justin? Yep, okay. Do I have that here? Maybe not. Okay, so increase ox equivalent. So this is where we want to get rid of the polygate depletion effect. And so we want to go to metallic gate electrode materials. So that one way is to use a metallic gate material to eliminate the polygate depletion effect. What's another way that some of you might have heard to enhance the oxide capacitance or per unit area? Right, so scale down T ox, or yeah, okay, T ox. Maybe let's call it X0. Okay, but what happens if X0 is too small? So let's look at C ox nominally is equal to epsilon, the dielectric permittivity divided by the dielectric thickness. So we can, yes, scale down X0, but tunneling limits this. Basically, if you physically make the dielectric too thin, it's not going to be a good insulator. You can have quantum mechanical tunneling of carriers through it. So this on the order of, depending on how much current you can tolerate in your gate, so it's definitely going to be greater than 1 nanometer. Okay, so you cannot scale the silicon dioxide layer to be thinner than a nanometer. Otherwise, you'll just get too much gate leakage current. Right? A MOSFET, ideally, you don't have current flowing between the gate and the channel. Okay, so what's another thing that the industry has done? Right, so use a high permittivity dielectric. So today, I think it's some kind of metal oxide. So hafnium dioxide, it's hard to say, because these are relatively thin also. It's only still a couple of nanometers thick. But you have higher permittivity, right? So you have more oxide capacitance. The relative permittivity of hafnium dioxide is actually some kind of X. It's not necessarily 2. It's, let's say, greater than 12. Sorry, this is relative permittivity is greater than 12. It's hard to say because they're so thin that they're not purely hafnium oxide. It might be mixed with some silicon dioxide. Okay, so what Intel has done, so Intel was the first to use what they call high K metal gate technology. They introduced high K and metal gate stacks at the same technology generation. That was introduced at the 45 nanometer generation of CMOS technology. Okay, and today we're at 22 nanometer. So that was in the middle of the last decade. Okay, what's another way we can improve the subthreshold swing? Ah, very good. Okay. Depletion capacitance. So what do you want to do? We want to decrease the depletion capacitance. Okay, so how do we do that? Increase the width of the depletion region. And how do you do that? You can change the doping in the channel. So how would you change the doping in the channel? Decrease, right? So you can decrease the channel doping, or the channel slash, yeah, let's say channel doping. Okay, so next time, well, next week we're going to talk about some trade-offs here. So yes, you can decrease the channel doping and you can get steeper subthreshold swing. But there are trade-offs for short channel devices. So we'll cover that next week. Okay, there's one more way. Looking at this equation, what else can you possibly change? Yes, John? Okay, change the operating temperature. Now, you want S to be minimized, right? You want to minimize the gate voltage swing. So you decrease, right? So you decrease temperature. Good. So what happens to the threshold voltage when you decrease the temperature? Goes up, right? Okay, so, but it doesn't go up as fast. I mean, it's not directly linearly proportional to temperature. So overall, yes, it does improve the subthreshold swing. So you can, so this allows you to design your transistor to operate with lower threshold voltage. So that's very good. It turns out that mobility also is dominated by like lattice scattering, and so if you lower the temperature, this is also good for increasing the effective mobility. Okay, so you can actually, if you decrease the temperature, you can have steeper subthreshold swing. So that means you can design your circuits to operate with lower VT, so you have higher current, faster speed, and the fact that the effective mobility improves also causes your circuits to operate at high speed. So see, there are computers in the, I don't know if you've heard of like Cray computers. They operate electronic circuits at low temperature to get higher speed, higher performance. Okay. So overall, what was the purpose for getting steeper subthreshold swing? Is to lower power consumption, right? So you can have lower off-state leakage for, let's say, a given on-state current. Okay, but if you need to apply energy to cool down your circuit, then overall, yes, it's probably not likely that you're going to save power overall. Okay, so that's it for digital logic. Just looking at basic considerations for designing a transistor to meet performance requirements. So generally for speed, digital circuit speed, you need to meet some minimum on-state current, and to meet some power, a maximum power consumption requirement or limit, you want to minimize the off-state current. So that means, so basically for VT, you have to be careful to optimize the design of your transistor and therefore tune the threshold voltage to meet both the maximum off current tolerable and meet the minimum drive current required for this required circuit operating speed. So your design project basically specifies that you have to design a MOSFET 25 nanometer gate length with some minimum drive current and some maximum off current. Okay? Okay, so that's for digital logic. For an amplifier, let me just draw simply, say, an NMOS device. Let's say you have some gate to source bias voltage, and then you have some small signal voltage that's time varying like this. So this is DC voltage, and you have some voltage signal here. Like maybe it's an audio signal or something. And let's just say you have some load resistor here connecting the drain of the NMOS device to a supply voltage. Okay? So the output signal, or the output voltage will be equal to some steady level, depending on VGS, plus some output, some small signal, some time varying output signal. Okay? So the small signal model of a MOSFET, and usually when we use a transistor as an amplifier, we are operating the transistor in the saturation region. Okay, so that's important. So, for digital logic, you're switching through the linear and saturation and off-state regions. But for amplifiers, generally we try to, most of them operate with the transistor operating in the saturation region. Okay, so if we actually apply a small signal, additional small signal gate to source voltage, we will get some change in the output current. So ID, right? If the gate to source voltage is changing due to this AC signal, then the drain current will also have a small change that's time varying. So the small signal model simply tells you, okay, what change in the drain current are you going to see for a given change in the gate voltage? Okay, that's why it's called small signal. Okay, it's only for small changes. So just keep in mind that little I, little d means a change in drain voltage. Little v, little g means a change in the gate voltage. Okay, so the simplest model is a small signal model is just shown here on the left in the middle. There's ideally no current that can flow between the gate and any other terminal because of the oxide. So basically it's an open circuit at the input. But the gate voltage does affect the drain current that flows. Right? So if the gate voltage changes by a little bit, by Vg, then the drain current will change by some amount, which is equal to Gm, the transconductance. So this is defined to be, or this is the definition of the transconductance. Gm is defined to be the change in the drain voltage, given by the equations we've looked at earlier, for a given change in the gate voltage. So dId, that's really the same as, this is equal to little I sub little d, and dVg is just, by definition, is little vg. Okay? So transconductance, all right, so if we take the equation for the drain current in the saturation regime and we differentiate it with respect to Vg, we get this formula for the transconductance. Okay, so qualitatively, let's look at this. If you have high transconductance, that means you can have a large change in drain voltage for a small change in gate voltage. Okay, so that's true if you have good capacitive coupling between the gate and the channel. That's true if you have a large current that's flowing in the first place. So small changes in gate voltage are still going to result in large changes in current. So W and mu effective, if you're operating at a high current level to begin with, small changes in the gate voltage, well, percentage-wise, it'll change roughly the same. But since you're operating at a higher current level, the absolute change in current is large. And of course, it depends on, again, on the current level that you're operating at. So that's VGS minus VT. That gives you the inversion charge density. OK, so that's a transconductance. So that's the ideal case for a MOSFET. If you change the gate voltage by a little bit, you should see a change in the drain voltage. And the larger the change in the drain voltage, the more gain you can have in the output signal. Okay? So if ID is large, then the change in the voltage drop across this resistor can be large, and therefore the change in the output voltage, this V out can be large. So then we say that this device, so the magnitude of the change in V out divided by the magnitude of the change in V in, if that's a big ratio, then you have high gain. Okay? All right, but the output, the drain current can also change if there's a change in the drain voltage. Okay, so let me explain why that's the case. If we look at the DC, I'm going to exaggerate. Okay, what is this effect here in the saturation regime? Channel length modulation effect. Okay, so notice if we're changing, okay, so if we have a change in the gate input voltage, the gate voltage, then that means we're going to have a change in the drain current. That means we have a change in the voltage drop across RL, therefore a change in the output voltage. But this output voltage is also equal to VDS, right? So if we're changing VDS, okay, so let's say we're operating here, with this, due to this DC, we're operating here. If we change the drain to source voltage because of the applied input signal, okay, that means we're operating around here. So VDS, any change in VDS will automatically also cause a change in the drain current as well, right? So basically, we also have to account for that. Okay, so the change in drain current is going to be equal to the change in drain current due to a change in the drain voltage, plus the change in drain current due to the change in the gate voltage. Okay, so that's it. So I have to tell you, qualitatively, this is bad. G sub D, we never want to see the output voltage change, the output current really be a strong function of the output voltage. And why is that? Well, I'll tell you. We want to maximize this, right? So for a given input gate voltage signal, we would like to maximize the change in the drain current to maximize the gain. Okay. Qualitatively, this is actually an inverter circuit as well. So if the input gate voltage increases, the output current increases. So the voltage dropped across the resistor increases. That means the output goes down. Okay? So this is going to be negative. VD, it's actually the change in drain voltage is actually negative for a positive change in the gate voltage. Okay, so that means you're actually lowering the change in that drain voltage. Does that make sense? So for a given change in the gate voltage, you're not going to get as much change in the output, the drain current, if you have a significant GD, significant slope. Okay? So ideally, GD should be very, very small. So we want this to be small. In other words, we want this to be flat. Right? We want the change in the output current for a change in drain voltage to be small, to have maximum gain. Okay, this is just, okay. Oh, and then if we operate, so if this signal is changing at high frequency, so remember okay, the current, if we'll see dV, dt. Okay, so if you're changing the gate voltage at a high rate, like dV, dt is really fast, and you want to charge and discharge your gate capacitance, or any capacitance in your transistor, you're going to have to flow more current, instantaneous current, right? Because if you want to change voltage more quickly, you have to flow more charge per unit time. So the current flowing due to charge or discharge capacitances becomes significant. You can't ignore them. So at low frequency, we could ignore those capacitances. At high frequencies, if you're looking at voltages that are changing very quickly, then you cannot ignore those capacitances in the transistor. So that's just shown here, right? The gate to drain, there's always going to be some overlap. So in an MOS structure, you have the gate electrode, but there's always some overlap between the gate electrode and the source and drain regions, and also there's fringing electric fields. So this diagram just shows you all the parasitic, non-desired capacitances that actually exist in a real transistor structure that you would have to take into account if you are looking at a small signal, if you want to calculate the gain and at high frequencies. So if you go to really, really high frequencies, eventually the amount of current that you need to flow to the amount of current that's left at the output, so you'll have more and more current that's just used to charge and discharge these parasitic capacitances, and eventually you're going to get no gain. Okay, so so qualitatively, there's going to be some frequency at which the gain becomes 1, and if you go to higher frequency, you're not going to get any current gain. So that's defined to be the cutoff frequency. Okay, so this is a simple equation just accounting for the current you need to charge, the input current you need to provide to charge and discharge the gate capacitance to change the gate voltage. And then the output current, just GM times VG. We're ignoring we're assuming ideal 0 GD. Okay, so we take the ratio of the output current to input current, we get this equation here. And if we set that equal to 1, we can find that the frequency, the cutoff frequency is going to be given by this equation here. Okay, so let me just end by very qualitatively pointing out qualitatively that this is 1 over the drift time. That's of the transistor. Okay, so what I mean is that you have a MOSFET. Okay, in the on state, right, it's biased in the on state. How long does it take for an electron to drift from the source to the drain? Well, it's going to be equal to the drift velocity divided by the channel length, roughly, right? Okay, so that's equal to the mobility times electric field, but this is in saturation, right? So that's VGS minus VT over M L, and then you have, so VGS minus VT over ML, that's the lateral electric field. And then you have this L over here already, so you have squared. So does that come out right? Right, okay. So basically, it tells you, interestingly, qualitatively, that the transistor is not going to work well if you try to operate, make changes in the voltage, and you need to have plenty of time for carriers to even just to flow across the channel and back, right? Okay, so that's just qualitatively. Okay, I think that's it. So if you haven't picked up your quiz yet, please come up and get it from me. And we'll continue with short channel devices, transistor scaling. So now next week we'll look at what happens when you make the gate length really, really short. Okay. Oh, yeah, because obviously the higher the cutoff frequency, the better. And the shorter the channel length, the better. But there are going to be challenges when you go to short channel length. So that's why we're covering that next.